Hi everyone, this is Sunita, Assistant Professor EC Department, Siddhartha Academy of Higher Education, deemed to be University. In this lecture, we will see different types of diodes, Zener diode, light emitting diode, varactor diode, and photodiode. So Zener diode. All these diodes are nothing but PN junction diodes. There is a slight differences. So Zener diode is nothing but PN junction diode, but heavily doped. The Zener diode is heavily doped when compared to the PN junction diode. Due to the heavily doped, the width of the depletion layer is very thin, and the breakdown in the reverse voltage, the forward characteristics are same as PN junction diode characteristics, exponentially increases, and the main difference is in the reverse bias condition. In the reverse bias condition, as the width of the depletion layer is thin, the reverse breakdown voltage occurs earlier. The breakdown voltage occurs earlier. After the breakdown voltage, it maintains the constant voltage. Whatever current, how much current, reverse current flowing through this, it maintains, it gives the constant voltage. So Zener diode mostly used in reverse bias condition after the breakdown voltage. The common breakdown voltage is 1.8 to 200 volts. So see, forward characteristics here, the forward characteristics are same as PN junction diode. Applied potential is increases, the current to the diode increases exponentially. Coming to the reverse voltage, the certain point, the breakdown point, the voltage is uh, how much current, reverse current increases, the voltage is constant. So it acts as a constant voltage source in the reverse bias condition after the breakdown. So in due to the heavily doped, the reverse current in terms of the milliamperes only. The forward current milliamperes and reverse current milliamperes. But in PN junction diode, the forward current in terms of the milliamperes, the reverse current in terms of the microamperes in PN junction diode, but in Zener diode, the reverse current in terms of the microamperes. Here, the avalanche breakdown will occur. See here, the ideal Zener diode and representation. This is positive, negative. This one is positive, this one is negative. Anode and cathode. Reverse voltage VR, reverse current IR in terms of the milliamperes. So reverse current, this point increases. This point's breakdown occurs. After the breakdown, it maintains the constant voltage. The rate of change of VZ, the rate of change of IZ gives the impedance, Zener diode impedance in the reverse bias. The main applications, the applications of the Zener diode is voltage regulation. Voltage regulation. Voltage regulators, whatever, irrespective of any changes in the input current, input voltages, the output voltage must be constant. Irrespective of any changes in the input current, input voltages, the output voltage must be constant. For that circuits, if you connect a Zener diode in the reverse bias and after the breakdown voltage, the voltage across the Zener diode is constant, whether irrespective of any changes in the input current and input voltage. So for that purpose, the voltage regulation Zener diodes will use in the reverse. There are the two conditions. One is Zener diode should be connected in the reverse bias condition. Reverse bias means Zener diode positive terminal should be connected to the battery negative. Zener diode negative terminal should connected to the battery positive. So in clipping and clamping circuits, PN junction diode are also used in clipping and clamping circuit for reference voltage, above the reference voltage, below the reference voltage. Like that we will use the Zener diode. Acts as a fixed reference voltage source. So after the breakdown voltage, we can use as this Zener diode as a reference, fixed reference so voltage source. Next, we will see the light emitting diodes, LEDs. Everywhere we will see LED in traffic lights, our some small experiments and kids' toys. We will see the LEDs. light emitting diode, nothing but PN junction diode. PN junction diode in the forward bias condition. When PN junction diode is in the forward bias condition, so the electrons will move to conduction band, from valency band to conduction band. Conduction band is the high energy levels. The electrons are unstable in the higher energy levels. They come back to valency band and recombine holes here. So while coming back to higher energy level to lower energy levels, the electrons release that energy in terms of the light, that release in terms of the light. So for germanium and silicon, that energy is unable to visible. So for fabrication of the LEDs, um, only gallium arsenide, gallium phosphide, these type of materials will be used for the making of the N-type and P-type materials. Normal, if you use normal silicon and germanium, that much amount, the amount energy released like as a heat. If you want energy, that much of energy in terms of the light, so for LED we need light energy. So for that purpose we will use the gallium arsenide, gallium arsenide, gallium phosphide, like that. For different we will see the LEDs different colors: white, green, red, yellow, orange, like that, different colors. For different colors we will use the different type of materials. For example, gallium arsenide is for one color, gallium phosphide is one color, like that. So LED, name itself, light emitting diodes. The LED emits the light. That means it converts electrical energy into the light energy. LED converts electrical energy into the light energy. See here, PN junction diode is in the forward bias condition. The conduction band electrons are unstable and they recombine with the holes in the valency band by emitting that energy in terms of the light. So here the electrical energy, positive battery electrical energy, is converted into the light energy. That light energy is directly proportional to the electrical energy, whatever applied voltage. If you are increasing the applied voltage, light energy increases. So this is the symbol for the LED. Normal PN junction diode, it emits the light. So the arrow mark, the arrow, it indicates the light. So emits the light. So light releases from the junction. So from the junction, this is the symbol of the LED. So forward bias condition. So x-axis current, forward current. How much forward current increases? The radiated light, the output light. The output light also increases. Linearity. There is a linear relation between the applied voltage and the forward current and the light, output light. These are the different structures of the LED. Mostly we will see like this in the kids toys, like that, and like lab experiments we will see this type of LEDs. Different colors come from the different materials. The fabrication materials are different for the different colors of the LEDs. The life of the LED may be in terms of the 1 lakh hours, like that. So next diode is varactor diode. A varactor diode, the same, the PN junction diode in the, but connected in the reverse bias condition. When PN junction diode is in the reverse bias condition, there is a depletion layer width increases. There is a formation of the depletion layer when PN is formed. So in reverse bias increases, the width of the depletion layer increases. So the depletion layer acts as a capacitance, dielectric material, immobile, lack of depleted from the charge carriers. So p side holes, n side electrons in between dielectric material acts as a capacitor. So this width, the depletion layer width is W. So the capacitance is inversely proportional to the width. So whenever increases the reverse voltage, the width of the depletion layer increases, that capacitance value decreases. So this is the main operating principle of the varactor diodes. See here, so PN junction diode is in the reverse bias. P type is connected to the battery negative, N type is connected to the battery positive. So in reverse bias, this is the junction. So this is the width of the depletion layer. Just formation of the width of the depletion layer. Holes and electrons, immobile charge carries a depletion layer dielectric material. It acts as a capacitor. This capacitor is variable capacitor. And the width of the depletion layer varies the value of the capacitor. So the C value is inversely proportional to the this width dielectric difference nothing but the width of the depletion layer. Whenever we increase the reverse bias potential, the width of the depletion layer increases. The width of the depletion layer increases. As a result, the capacitance value. The capacitance value is depends upon the width of the depletion layer. If the W is increases, capacitance value decreases. Variable capacitor. So the capacitance value is varied by the applied voltage, reverse bias voltage. So reverse bias voltage increases, width of the depletion layer increases, capacitance value decreases. The reverse voltage decreases, width of the depletion layer decreases, capacitance value increases. Inversely proportional. So the capacitance can be varied by changing the reverse voltage in the reverse bias voltage in the PN junction diode. This is the main principle. This is the symbol. This is the symbol for the varactor diode. So variable symbol and the equivalent circuit. Equivalent circuit, the internal resistance and the variable capacitor. So variable capacitor. See here, greater reverse voltage. Reverse voltage is very high. This is the less reverse voltage. Reverse voltage increases, the width. See here, the width of the depletion layer increases. Capacitance value decreases. See here, the reverse voltage is less amount, less applied voltage. So the width of the depletion layer is less. The capacitance value is more. The capacitance value is more here. So this is a graph reverse voltage and the capacitance in terms of the picofarads. Reverse voltage increases, capacitance value decreases. Reverse voltage is minimum, the capacitance value is maximum. As reverse voltage is increases, the capacitance value decreases. So these are the applications of the varactor diodes, voltage controlled oscillators. So here capacitor, variable capacitor operation mainly the voltage is control the capacitance value. So voltage controlled oscillators. So RF and microwave frequency tuning. So the frequency changes, the capacitance value also changes. And the capacitance changes, frequency changes. So that's why. So tuning the frequency to tune the perfect frequency, we will use the this type of varactor diodes. By changing the applied voltage, by changing the reverse applied voltage, width changes, capacitance value changes. As a result, frequency changes. Uh, in frequency modulation, automatic frequency control. So till now we have seen Zener diode operation, characteristics and applications, LED operation, characteristics and applications, varactor diode, characteristics, operation and applications. The last one we will see here, photodiode, photodiodes. So this is the quite opposite in like LED, quite opposite to the LED. LED is light emitting diode. It emits the light. That means the LED converts electrical energy into light energy. P-N junction diode is in the forward bias. So all the points are exactly opposite to the photodiode. When P-N junction diode is in the reverse bias. P-N junction diode is in the reverse bias and it converts light energy into electrical energy. It converts light energy into electrical energy. How we will see here. The photodiode is operated in the reverse bias. They typically have the small window to let the out. So here the PN junction diode is in the reverse bias. P-type terminal is connected to the negative terminal of the battery. N-type is connected to the battery terminal of the positive. The battery terminal or positive terminal of the battery. So whenever the light is instant on the junction, so light energy as an input, output is the electrical energy. Whenever the light is instant on the junction, so a photons collide these covalent bonds and release the electrons. These electrons will get energy, and they move and break the other covalent bonds. These electrons, like that, the avalanche, multiple electrons will release. That flow of electrons cause the flow of the electrons cause the current. So here the light energy is converted into the electrical energy. This is the symbol opposite to the LED. Same PN junction diode. LED light emits arrow mark outwards. Photodiode light energy is the input energy. Arrow mark inside the junction. So these are the devices, device structure, physical devices of the photodiodes. See here, the x-axis radiance, reverse current. So while we are increasing the illumination, light energy, the reverse current increases. Thus, a directly proportional linear relationship. Here we will observe there is a small amount of current irrespective of the radiance. Even the illumination is zero. That means there is no light fall on the junction, but there is the existence of the small current, reverse current, because of the due to the movement of the minority charge carriers. PN junction diode reverse bias, there is a movement of the minority charge carriers. That movement of the minority charge carriers holes in N side, electrons in the P side. Due to that minority charge carriers movement, there is small amount of current. So reverse current. This current is called the dark current. This current is called the dark current. The current produced at the zero illumination. In the absence of the light energy, the current is called the flow of the current is called the dark current. After that, the illumination is increases, the current increases. Illumination increases, the current increases, linear relation. So in this, the photodiode is used as a sensor. So in a factory, fabricating some items, it needs a count per hour how many items are fabricating, how many items are going to deliver, or per day how many items. So for that purpose, see, this is the light source, this is the photodiode. In this photodiode is connected, this is the light source. Light source incident on the photodiode, there is a current. So whenever object comes here, whenever object goes through here, there is no light on the diode. So the current is equal to dark current. The current is equal to dark current. We will write a program like that. Whenever the current is equal to dark current, count is increases. Like that, how many items, how many times of dark current indicated, that that is the count of the items fabricated in a hour, in a day, like that. So we will use light detection and measurement and optical communication systems, safety and security systems in like in the bank, ATMs, museums, like that. If you place that light source at photodiode, whenever the light is not instant on the photodiode, the current is equal to dark current. Whenever the dark current is detected, alarm should be uh, warn the sound or light, anything like that. We can use the security systems, and barcode and QR code scanners also we will use the photodiodes. So these are the symbols for the different diodes. If this is the, like a normal PN junction diode acts as a rectifier switch, like that. Normal PN junction diode, this is normal PN junction diode. So this one is the GNAT diode. This one is the GNAT diode. The symbol is Z, and cathode type symbol is Z. So this is the varactor diode, variable capacitor varactor diode. This is a LED, light emitting diode. Light is the output energy. Electrical energy is converted into the light energy. Light emits, so light is outward. This is the photodiode. So photodiode is this symbol also. Photodiode means it input energy is light, output energy is electrical energy. It converts light energy into electrical energy. So the arrow mark into the junction. So this is about the different diodes discussed in this lecture. Thank you.